Hello, and welcome back to my YouTube channel. My name is Professor Gavala, and today I'm going to be talking to you about frequency response. And essentially, this is going to be an overview of frequency response, why we need it, what it is, and what it's needed for, the type of applications it's needed for. So specifically, we're going to be talking about the objective of frequency response, the motivation of frequency response, and we're going to dive into a little bit of circuit theory concepts. And these concepts are just going to show us why we need the frequency domain and what it's used for. So, and on the screen we see here are what we consider a low pass filter, a high pass filter, a band pass filter, and a band stop filter or a notch filter. And essentially, we're going to draw a schematic for the low pass filter and the high pass filter. But in this video, we might not get to the band pass filter and the band stop filter. But essentially what this means is as I increase my frequency, omega, again, remember omega is equated to 2 pi f, or 2 pi times regular frequency, and it's in radians per second. As I increase omega, my low frequencies are going to go through, but my high frequencies are going to be attenuated. And again, we'll dive into specifically what that means. So to begin, what is my objective? The objective is to determine the speed limitations of a circuit or of circuits. And this means how fast can my circuit run? What does the circuit do as we increase the frequency? And an example of this, as you can imagine, is if we take a signal from 0 to any time t, and let's just say at 1, it increases and drops at 2. Let's say this is Vn or Vp is equals to Vn. And we put it into an amplifier. Let's just say this is equals to 1. And this amplifier shoots out a V out. And we have two situations. The first situation is at 1, it reacts exactly the same as my input. So this is Vp, maybe it's amplified to 20 volts. This is equals to V out. And at another situation 2, we see that at 1, it starts to rise up, and then at 2, it starts to drop down. Okay? So this is what we call a fast amplifier. Okay, because it's responding exactly like my input at the output. And here we call this a slow amplifier. So the whole purpose of frequency response, or our objective, is to determine how fast or how slow the circuit is, or how many cycles per second. So for example, if you remember this from physics, your velocity, or the meters per second, is equals to your frequency. Again, this is in 1 over seconds times your wavelength, or this is just meters. All right. So again, frequency in this case would be V over lambda, which is equals to, or which the units are meters per second over 1 over meters. So then this is just V over lambda. 1 over seconds is the units. Or again, we represent this as hertz. Another way to visualize this, which again, in terms of the speed of a signal, is if I take 1 second and I say my signal, my wavelength, I have one signal over a span of 1 second. This is a slow signal because in 1 second, I only get one cycle per second. Another example of this would be, imagine if I have 5 cycles, so 1, 2, 3, 4, 5 over 1 second. So this is a faster signal. So this is going to be 5 cycles per second. So again, this is what I mean by the speed of my signal increases, right? As it increases, how do I expect my signal or my circuit to react? Is it going to react slow, right, like here, or is it going to react fast, like here? So I hope this motivation or this objective makes sense. Now, let's go to the motivation behind this. Why do we need this? So let me call this the motivation, or again, why this is needed. Again, when I say this, I mean frequency response. And essentially, it's because high-speed circuits are everywhere. And again, this is simply just because we want to do things at a fast rate. You don't want to be waiting for you're on the phone call or something, or you're trying to download a video and it's taking days or months to perform. So we want everything to be happening in a high speed rate. And some examples of high speed applications is, if you're listening to this video on YouTube, chances are you require Wi-Fi. And Wi-Fi runs at 2.4 gigahertz to 5 gigahertz. Again, imagine in this range of 1 second, I have a signal that is fluctuating, that has a wavelength of 2.4 billion cycles per second. All right. Again, that's almost impossible for me to draw on the screen, but I hope you can visualize how high of a speed that is. Another example of this, if you're listening to this using some headphones, this could be considered using by Bluetooth. Imagine if it's wireless, which resonates around 2.4 gigahertz. If you're in your car and you listen to this while you're driving to your friend's house, you might be using the GPS for direction, and GPS resonates around 1.5 billion hertz per second. If you're driving an automatic car, the chances are it's using automotive radar. I meant an electric car. This resonates around 26 gigahertz to around 75 gigahertz. So it's extremely fast. And if you've ever done a project using a microprocessor, you're looking at 4 to 5 gigahertz. Again, these ranges are what we consider to be radio frequency waves, or radio waves in terms of the electromagnetic spectrum, which range from 300 kilohertz to around 300 gigahertz. All right, so anything in this range will be considered a radio wave. So in order to build these applications for these high-speed signals, we need to understand which type of circuits will allow for these high-speed signals to pass through, and which type of circuits will attenuate or not allow these high-speed signals to pass through. So that is the motivation and the objective of frequency response. Now, in order for us to see different examples of frequency response, we need to understand some circuit theory concepts. And you might have learned this in your Circuits 1 or Circuits 2 class, so it might be a refresher. But let's go ahead and talk about circuit theory concepts. And I'm going to make a table I'm going to call this time domain. And I'm going to call this frequency domain. And essentially what we want to accomplish here is, why do we need the frequency domain? Or what is the frequency domain? And why do we use it? So let's consider our first example. Imagine you have a voltage. It could be a sinusoid, V1, going into a capacitor, C1, and there's a current, I1, flowing through it. Let's write some equations in the time domain about this circuit. So we can say that I1 is equals to the value of the capacitance of the capacitor times the change in voltage over time. All right. If you wanted to solve for the voltage across this capacitor, so let's say VC, in this case would also be V1. So VC, which is equals to V1. Remember, it's going to be 1 over C1, the integral of I1 dt. All right. So this maps to that. In the frequency domain, however, what we do is we consider this to be an impedance. All right. We consider that to be an impedance, and we simply say that I1 is equals to C1 times J omega times V1. You can also write this as C1 J omega is equals to S times V1 is equals to I1. If you wanted to write the voltage V1, it's going to equate to I1 over C1 times S. All right. So again, something we should realize here is that we're dealing with an integral here, but here we're dealing with an algebraic style functions, right? And again, this should be AIC. As a result, this is a little bit easier to work with, right? These are divisions and multiplications, as you see here and here, but these are derivatives and integrals, which are a little bit not as nice as we put it. All right. So let's go to our second example. Let's go ahead and say, okay, imagine you have a AC signal going into a resistor and a capacitor. Let's call this C1 and R1. And let's say that this here is I1. So let's go ahead and write some equations for 2. We will say that let's write a mesh equation through this mesh here, or through this circuit. We can say then that V1 is equals to the voltage across this resistor, which is simply R1 I1, plus the voltage across this capacitor, which again is 1 over C1 integral I1 dt. All right. And we can write the same thing in the in the frequency domain as V1 is equals to R1 I1 plus I1 over C1S. Again, as you can see, this is an integral. This is a division, which is easier to work with. All right. Let's take our last example, or our last circuit. It's a similar circuit, but this time we're going to solve for V out. All right. So this is C1. This is V out. This is R1. And we have a current I1 flowing through it. Let me go ahead and solve for I1. I1 is equals to C1 times the change in V out over dt. Again, if you don't remember how I'm getting this, I have a playlist called Circuits 1. I talk about how to find the current through a capacitor in those playlists. So let's go ahead and write out some equations. So here we can say that Vn, again, I'm just writing a mesh loop, is equals to R1. I1 again is here. Okay. So I'm just rewriting this, but I'm replacing I1 for this right here. I hope that makes sense. So this is C1 d V out over dt plus simply put V out. And essentially, this is what we call a first order differential equation. A first order differential equation, and using the 5, which is final, initial, final, exponential, you saw that V out is equals to Vn 1 minus e to the negative t over tau, where again tau is equals to RC. And the transfer function, which is V out over Vn, is equated to 1 minus e to the negative t over tau. Again, I hope you're realizing and seeing how much more complex this is in the time domain. Again, you have to know differential equations. You have to remember your 5 or how to prove your 5. And you have to know that tau is equals to RC. There's a lot of different things in order to find this, what we call the transfer function, or the V out over the V in. But if we did it in the time domain, let's see how easier this is. So for 3, I'm just going to take a voltage divider at V out. I'm going to say V out is equals to the output impedance, which is simply 1 over C1s over 1 over C1s plus R1 times Vn. And doing some, deleting denominators and combining terms, we get that V out is simply equals to 1 over R1 C1s plus 1 times Vn, where the transfer function V of s is equated to, actually I made a mistake here. This should be the transfer function V of t. So the transfer function here, V of s, is 1 over R1 C1 s plus 1. Again, this is V out over Vn. So as you can see, this is a lot easier, right? If you know your voltage divider equation, you can easily implement this and go ahead and divide the V in over the V out, V in by V out, and you get your transfer function. Only 3 steps. So as I mentioned before, we'll normally be using a sinusoidal signal. So H of S is essentially equals to H of J omega. So again, this can be rewritten as 1 over 1 plus R1 C1 omega J, just to make it, or just maybe consistent, J omega. All right. So a little bit from circuit theory, from complex number 3. If you have a function x is equals to a plus b j, the magnitude of that function is equals to the square root of a squared plus b squared, and the angle of that function is the tan inverse of b over a. For now, we'll just focus on the magnitude. And again, remember, this is from complex number theory. All right. So in our example here, for h of s, or h of j omega, we could say that the magnitude of h of j omega is simply the square root of 1 squared plus 0 squared. Again, imagine that this is a plus 0 j, okay, divided by the square root of 1 squared plus, this would be R1 C1 omega all squared. Again, because it's the j term is composed of R1 C1 and omega. And essentially, we can then simplify this to just be 1 over the square root of 1 plus R1 squared C1 squared omega squared. And that is your transfer function. Now, let's go ahead and plot this to see what's actually happening. And then we'll analyze the plot to extract some meaningfulness from it. So if we have our plot that looks like this, and this is omega, again, this is in rads per second. If you wanted to map this to frequency, which is in hertz, you would do omega divided by 2 pi. All right. So essentially what we're saying here is in my magnitude function, if I input a 0 for W or for omega, I would get 1 over the square root of 1 plus 0, right? Because this term goes to 0. So then this just becomes 1. So I get a 1 from a magnitude. And if I input infinity, so 1 over the square root of 1 plus infinity, this becomes 1 over infinity, which is then equals to 0. So as I go to infinity, this goes to 0. All right. So what I'm going to look at now is a circuit that kind of goes like this. And what this means, again, because this is very, very important, is that as I increase my frequency, my response goes from being very, very fast, and then it starts to drop, and then it becomes very, very slow. Again, if you want to see it visually, it's similar to what we talked about here, where in the low frequency ranges, if you give me an input like this, my output will be very, very fast. And if you give me an input like this in the high frequency range, my output will be very, very slow. So that's basically how you can visualize this. Okay, so that's what a low pass filter is telling you. Again, this is a low pass filter. Or again, this is an RC filter. All right. Again, it looks something like this. Okay. This is V in and this is V out. Some key things to note is when you're doing filter design or frequency response, there's something called a cutoff frequency, FC. This is a very important frequency in this situation. It's 1 over R1 C1. And let's go ahead and plug in omega is equals to R1 C1 and see what happens in my equation. So I get 1 over the square root of 1 plus R1 squared C1 squared times 1 over R1 squared C1 squared. As you can see, this becomes 1. So then I'm left with 1 over the square root of 2. This becomes 0.707. And again, if you wanted to talk about it in terms of dB, you get 20 log 10, 0.707, which is minus 3 dB. All right. So in a lot of engineering applications, you're gonna hear about cutoff frequency and the minus 3 dB location. All right. Very, very important. And the reason why is because this tells us what we refer to as the bandwidth of my circuit. So the bandwidth is the frequency range across which the input signal will go to the output. All right. So this here is called my bandwidth. All right. Again, that's very, very important. Cutoff frequency and bandwidth. And again, if you wanted to find your cutoff frequency of your circuit, you would equate your transfer function magnitude to 1 over the square root of 2 and solve for omega, and you would get 1 over R1 C1. Okay, so another example which I want to touch on is, imagine if you have an RL circuit, which is a resistor with an inductor. This is V out, this is V in. And essentially you will find out that using the voltage divider, again, the frequency range, again, this maps to LS, V out is equals to LS over R plus LS times V in. And the magnitude response of this function is simply what you consider a high pass filter. All right. So this is a high pass filter. Okay. So what this circuit is saying is that at low frequencies, V out is essentially going to be equated to 0. But then at high frequencies, V out is going to get there's going to be an induced voltage, right, at high frequencies, and this V out is essentially going to equals to V in. Okay. Just as a quick exercise, you can do it down in the comment section below. What would be the frequency response of a circuit that looks like this? Something like this. This is L. Let me call this L2, R2. This is V out, and this is V in. So what type of filter is this? What type of filter is this? And you can leave down your answer in the comment section below. And essentially, that's the general gist of frequency response. Again, it's extremely important. We didn't get to band pass filters and band stop filters, but essentially a band pass filter is when you want to stop the frequencies outside of this band range. And an implication of this is if you're in your car right now and you listen to the radios will say, okay, we want only a certain frequency to pass through. Let's just say 59.9 FM, right? Or let's just say 107.9 FM. And that goes through, and and all other frequencies are disregarded. So that's an application of a band pass filter. Again, if you like the video, please like it. Leave some comments down in the section. If you have any questions, please share the video. And if you like the content on this channel, please make sure to subscribe to the channel and share my YouTube channel. Thank you.